Hi guys, today we will see how to design and implement XOR gate and XNOR gate using this neural networks. So now let's start. First, let's understand what is XOR gate. Okay, so this is how a XOR gate looks like. So here how the truth table of XOR gate will look like is this is X1, this is X2 and this will be our Y. So let's write a truth table for this. So when it is 0, 0, that time it will be 0. When there is a 1 bit change, say it is 0, this is 1, so output will be 1. Again here 1, it is 0, 1 bit change, output will be 1. But if both x1 and x2, both inputs are same, then the output becomes 0. Now observe this truth table. From here we can understand. So here that both the inputs are same, so that's why we got output as 0. Here also both the inputs are same, output as 0. Here both the inputs are different, so we get output as 1 1. So this is how a basic XOR gate looks like, and this is the functionality. Now we have to design this for neural network. Now, as we saw in AND gate, OR gate, NOT gate, we were using perceptron there, which was nothing but two input perceptron. We were using this because we knew that all those gates, that is AND gate, OR gate, NOT gate, these are all what? Linear. Okay, these are linear logical gates. What does it mean? Linear logical gate means there we saw the truth table. There the output was becoming either 1 or 0 only for one condition. For rest of it, it was same. So it was linearly differentiable between the zeros and ones. Now here for two different conditions we are getting output as 1 and for two different conditions we are getting output as 0. So this is not a linearly separable model. So we can't say that XOR gate is a linear. Okay, that means our XOR gate is a non-linear logical gate. So we can't use perceptron here. Okay, because we will need some hidden layer or something inside it which will be working in a non-linear conditions correctly. Now how do we do that? Let's see. So here we saw that a single line cannot separate ones and zeros on a graph. So that is they are not linearly separable. So here that's why we'll be using something called as multi-layer perceptron. That is nothing but perceptron, but we will be adding a layer to it for the non-linearity conditions of this gate. Okay, so how we will do this? Okay, so here we'll be using this MLP with a one hidden layer. How many hidden layers we'll be using here? One hidden layer. Okay, now this we understood. Now for this, say first layer. Okay, so my XOR gate here will have now two steps. How many steps? Two steps. Okay. So here will be my first layer. Okay. So my first layer will be what? This will be used to compute my intermediate operations. What it is? Intermediate operations. Whatever operations we required for this non-linearity will be done here. And then the second layer will be combine the outputs which we got from here, okay, all together. So combine them to produce my XOR gate. So this is how it will be done. Now I hope this is clear. Okay, so XOR here will be following two steps. Okay, for first layer what we'll do is we'll compute the intermediate operations, and for second step we'll be combining them to produce a XOR gate. Now what are this first layer and second layer? Let's understand here. Now first let us see what is the mathematical representation for this XOR gate. Okay, then we'll come to this point. So the XOR for my inputs x1 and x2 can be written as x1 or x2. This operation, this is nothing but OR. This symbol stands for OR. So x1 or x2 and do AND of it with negation of x1 and x2. So this is the mathematical equation. Okay, this operation is what? AND. This operation is what? NOT. So here we are requiring three gates: OR, and NOT all together. So this is how a mathematical equation for XOR looks like. Okay, that is nothing but x1 or x2 perform AND with what? Negation of x1 and x2. So this is a mathematical equation. Now we need to design our neural network in such a way. That means what is happening here is, say I have one input x1, I have another input x2. First what is happening is x1 or x2. Okay, so here what I'll do is x1, Here I'll apply OR. Here we'll be taking AND in between. So one is OR operation. Okay, this is this. Another is what? Not of AND operation. Correct, no? Not of AND is called as NAND. Not of AND is called as NAND gate. Remember. Okay. What is not of AND? Nothing but NAND. So here this operation will say one is perform NAND and then give that to AND. Okay, and then this AND operation will give me the output, which is nothing but my XOR of x1 and x2. Okay, I hope this is clear. So this is a simple mathematics, and now we have to design my neural network in such a way. Now in previous lectures we saw that for OR what will be my equation, for AND what will be my equation, and for NOT as well what will be my equation. So in that way we'll find. So here we will be having three steps overall. Okay, what will be those? My step 1, that is first what? We have to compute OR, that is nothing but compute OR. For OR, we saw the equation, which was what? X1 W1 for two inputs is X2 W2 plus bias. Okay, this should be greater than or equal to 0 for the OR operation to be performed. So here we saw for OR gate W1 was 1, W2 was 1, and bias we took it as minus zero point 0.5. So putting that, what we have to satisfy for OR gate now? X1 plus X2 minus 0 0.5 should be greater than equal to 0. Okay. Now similarly, second step is what? Compute NAND. Now NAND is nothing but what? Not of AND. So let's write the equation for AND first. And for AND what it was? X1 W1 plus X2 W2 plus B. This should be greater than equal to 0. For AND we took W1 as 1, W2 as 1 and bias as minus 1.5. But now, as we are doing NAND, so everything will be the opposite of it, that is negation of it. So then my W1 will become minus 1. So what will happen is, instead of 1, I'll take minus 1. So this will become minus x1. Instead of 1, W2, I'll take minus 1. This will become minus, and then minus of minus 1.5, this will become plus 1.5. So for NAND, I have to satisfy this equation. Okay, so this is for NAND, this is for OR. Now these are the two steps, and then at the end what we are doing is we are doing the AND operation between this OR equation and NAND equation, correct? So here I'll be doing compute AND, which will be nothing but, say this, if I call this equation as H1 and if I call this equation as H2, then I have to perform AND operation between H1 and H2, correct? So how that will be? Now here my inputs and outputs we have defined. So my output is simply Y, but here my input will be now H1 W1 plus H2 W2 plus bias should be greater than equal to 0. For AND gate we are putting what? W1 as 1, so it becomes H1, W2 as 1 and bias as minus 1.5. This should be greater than 0 for AND gate. So these are all the computations which we need to design a XOR gate using this neural networks. So okay, I hope this is clear now. It might be quite confusing, so understand how AND gate, OR gate and NOT gates are working, how the weights and biases are set for them, which I have explained in the previous lectures. The link is provided in the description. So please go through the video explanation of how these gates work and then come to XOR. If you come directly to XOR, you might find it difficult, like how weights and biases are getting set for different gates like OR and then how we derived at NAND. So I hope this is clear now. Now let's see the neural network architecture for our XOR gate. Now first requirement which we know is our input layer. Okay, so this input layer has two neurons. What are those? X1 and X2. Then we have a hidden layer. Now this hidden layer again has two neurons. What are those? One will perform OR, one will perform NAND. Then third, what is that? Nothing but output layer. Output layer. What is that? Nothing but a output layer which will have just one neuron, that is what? Y. And then we have something called as activation function, which we require to activate our neuron to perform a certain task. So what is this activation function we are using here? As we saw earlier, whenever we use perceptron, this is the basic activation function which we can try. So we'll be seeing activation function as a step function here. So what it is, that is nothing but f of z will be equals to 1. If what? This z, whatever equation we are defining, is greater than equal to 0. Otherwise, we get it as 0. Okay. So this is how our neural network architecture is. Now let's draw a neural network. For input, we need two neurons. So I am taking two neurons here. Now this will be working as my x1 and x2. Then for hidden layer, again I'll need two neurons. And then for output, we need one neuron. Now here I'll be putting my inputs. So here this is x1 and this is my x2. This is for my OR gate and this will be for my NAND gate. And then at output we saw that was for AND gate. So now let's connect. Let the output of this be H1 and let the output for this be H2. Now we saw for NAND gate we were giving bias. What was the bias for NAND gate? We were giving exactly opposite bias which was given for AND gate, that is plus 1.5. So for AND gate it will be minus 1.5. And for OR gate, what is the bias? Minus 0.5. Now here it will be W from neuron 1, it is going to neuron this from 1 to 1, and then this will be W from 1 it is going to 2. Then this from 2 it is going to 1, and this it is going from 2 to 2. Now we know the values of each and every. So this is nothing but acting as my W1, and this is what which is going. So this will be again 1, because we know for this gate for input x1 w1 plus x2 w2, we go like this, right? Now my w12 will be minus 1. Why? Because it is coming on a NAND gate. We saw the equation for NAND gate. What it was? Minus x1 minus x2 plus 1.5, right? So plus 1.5 we have given, minus x2 means what? Weight is minus 1. Here also weight is minus 1. So whatever neuron connections are coming on NAND gate will have weight as a minus 1. So it is going on NAND gate, that's why it is minus 1. And this is also going on a NAND gate, so this is also minus 1. So now this is the overall neural network which is ready with us. Then we come here. This is nothing but my weight h with respect to 1, and this will be nothing but my weight h with respect to 2. So again for AND gate, what are my weights? 1, and AND gate weight is 1. This is nothing but my y. Okay, so this is how you can set the weights and biases. Again, I am stressing that to understand how the weights and biases are set for OR gate and AND gate or NOT gate, please refer to the earlier lecture videos in this playlist. You will get a better idea how these values are chosen for the weights and biases and why we are putting this here. So the links are in the description of this video. Please go and check it out. Now let's continue. So let me start now. Now as we saw, this is how our neural network will look like. Now let's write the equations. Okay. Equations will be what? For my hidden layers. That is, let's write for H1 and H2 first. For my H1, what it will be? It will be like this function, that is nothing but x1 w11 plus x2 and then whatever is coming on h1 w21 plus bias. This should be greater than or equal to 0. Okay, so let's substitute these values, which is nothing but f of what is my x1? X1. And w11 is what? 1. So this becomes x1. W21 is what? 1. So this becomes x2. And then my bias for h1 is what? Minus 0.5. So this will be minus 0.5. So this is how the equation of h1 is calculated. Similarly for h2, again we say f of x1 and then we get here w12 plus x2, here we get w22 and then plus bias. This should be greater than or equal to 0. So then my this equation, what it will become? My h2 will be something like f of. Now w12 is what? Minus 1. W22 is minus 1. And what is my bias here? It is plus 1.5, correct? Plus 1.5. This is the bias, right? For H2. For H2, this is the bias. For H1, this was the bias. So this is plus 1.5. So that I have taken here. Okay. So we have now H1 and H2 here. Okay. This is my H1 and then here I can see my H2. So now the equations for the hidden layers are ready. Now what will be my equation for this output layer? So my output layer equation will be something like Y, which is nothing but F of. It is for AND gate. Okay. So my W1 will be what? First let me write this H1 plus H2 WH2 plus bias. This should be greater than equal to 0. When I substitute the values, then my value should be something like y, which is equals to my WH1 will be 1 for AND gate. So this will be H1 plus H2 bias is minus 1.5. So this is greater than equal to 0. Now I have all my equations, that is nothing but H1, H2 and for Y. So these are the equations for my hidden layers which we need to follow, and this is the equation for my output layer. Okay. This is how you can design the neural network. Now we have these conditions here. Yeah. So now for designing purpose, we have the equations. Now you just have to write a code for these equations and then generate the output for a XOR gate. I hope this was interesting enough for you guys. Now for XNOR gate. Which gate? That is nothing but XNOR gate. XNOR is nothing but negation of XOR. Correct? So whatever output you get here, you just apply negation to it and you will get a XNOR gate. Okay. So this is our output. When I apply negation to this output, what will be the output for that then? After applying negation, my Y will become then F of minus H1 minus H2 plus 1.5. This should be greater than equal to 0. All other equations remain same. Just I have to change the Y equation. Just I have to change what? Y equation. This is nothing but a negation of Y which was for XOR. Correct? Okay, so this is how you get XNOR. So all the concepts, all the logics remain same just for this AND gate. Whatever output you are getting at Y, just apply negation to it and then from there you will get a XNOR gate. I hope this is clear. So what was the output for this XOR gate we saw was? XOR, which is nothing but function of H1 plus H2 minus 1.5. Okay, this should be greater than equal to 0. This was the equation for XOR. Let's see the truth table for XOR. Truth table. Okay, this was what? X1, X2, two inputs and one output. Okay, so for 0, 0, it's 0. For 0, 1, it's 1. For 1, 0, it's 1. And for 1, 1, it's 0. Now, to understand this, remember XNOR. Okay, how you can find a XNOR? Just by simply taking a negation of XOR gate. So XNOR is nothing but a negation of XOR gate. So you will get your XNOR. So then the truth table will become something like here X1, here X2, here we have Y. Now we have to just negate the values whatever we got for XOR. So for 0, 0 it was 0. So here it will be 1. For 0, 1 it was 1 there. So here it will be 0. For 1, 0 it will be again 0. And for 1, 1. So XNOR, what is happening is whenever both the inputs are same, we get output as 1 or else 0. So again XNOR is also a non-linear logic gate. So I have explained earlier what is linear and non-linear logic gate. So just remember this. Okay, XOR, XNOR, these are non-linear logic gates, whereas AND or NOT are the linear logic gates where they are linearly separable, linearly modeled easily. So now as we know that the equation, so whatever equations we derive for XOR, keep it as it is. When you have a final output, just apply a negation to that. You will get the equation for XNOR, which will be F of. Now negation means minus H1, negation means minus H2, and this will be plus 1.5. This equation should be greater than 0. So you have a equation to design a XNOR gate as well now. Okay. I hope this was fun learning and I hope you understand each and every concept here. Again, I am repeating that this to understand how the weights and biases are set. And this type of questions are very frequently asked in the companies where they are using AI in their hardwares. So it will be very beneficial for you to understand the concepts and implement the logic. In next video, we'll see how the code is implemented for both XOR and XNOR gate using neural networks. I hope you enjoyed this video. All the best for your practice, guys. If you like it, please subscribe my channel and keep sharing. Thank you.